All right, in this video we're going to connect the limit of a function with limit of a sequence, and so we're talking about a limit of a function as x goes to infinity. We're going to connect that with the limit of a sequence. So we have a theorem here that says let L be a real number, and suppose that the limit as x approaches infinity of f of x is equal to L. If the sequence a sub n is in agreement with the function at all the positive integers, so that, in other words, f of n is equal to a sub n for all n, then the limit as n goes to infinity of a sub n is equal to L. So for the proof, we're going to let epsilon greater than 0 be given, since the limit as x goes to infinity of f of x is equal to L, there exists an m greater than 0 such that f of x minus L is less than epsilon whenever x is greater than m. Since the natural numbers are unbounded, there exists a natural number n, capital N, and that n is going to be greater than m, and then for all n greater than capital N, the absolute value of a sub n minus L, so this sequence is also equal to f of n minus L, and that's going to be less than epsilon because n is greater than m, and once we were past m, the function and its limit was within epsilon. Okay, and that completes the proof here. We can draw a little bit of a picture here. Okay, so here's your function f of x. There's its limit. Here's L plus epsilon. Here's L minus epsilon, and then the sequence you can kind of think of it as a bunch of points on the curve, or ants on the log, or something like that. And so the sequence is following what the function is doing. The sequence is just not defined at every point on the real number line. It's just the natural numbers that's going to be defined. So here would be your m, and then your n would just most likely be a little bit further along the next positive integer. If n is a positive integer, then m could be equal to n. Okay, and so that's kind of the idea of what's going on. And so if we can find a function that agrees with our sequence on the positive integers, or the natural numbers, then we can convert things about sequences into things about functions, and we know a lot about doing functions and their limits, L'Hopital's rule, all kinds of theorems. So that's what we got going on the next page here. So limit properties for sequences. So if the limit of as n goes to infinity of a sub n is L, and the limit as n approaches infinity of b sub n is equal to k, then the limit of the sum or the difference is the sum or the difference of what their limits were. And that's a property right from limits of functions. The limit as n goes to infinity of a constant times a sub n is just going to be the constant times L, where c is a real number. The product, this is term by term, so a1 times b1, a2 times b2, a3 times b3. The limit as n goes to infinity of the product of a sub n times b sub n is equal to the product of their limits, L times k. The limit as n goes to infinity of a sub n over b sub n is equal to the limit of L over k, provided that b sub n is not 0 for all but finitely many n, and also the limit is not 0. We also have the squeeze theorem. If the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of b sub n, and those are both L, and there exists a natural number n such that for all n greater than or equal to n, a sub n is less than or equal to c sub n, which is less than or equal to b sub n. So the c sub n is sandwiched between a sub n and b sub n at some point onwards. Then if that's the case, then the limit as n goes to infinity of c sub n is also equal to L. Okay. We also have an absolute value theorem. If the limit as n goes to infinity of the absolute value of a sub n is going to 0, then so also is the limit as n goes to infinity of just a sub n is going to 0. Okay. And so let's go and look at the next slide, and maybe we'll do some applications here. So we're going to find some limits. So we're going to find the limit of each sequence. So we're going to look at finding the limit as n goes to infinity of 3 plus negative 1 over n. Now if we wanted to, we could look at negative 1 to the n over n in absolute value. Okay, now the absolute value of negative 1 to the n is going to be just 1, because negative 1 to the n is either going to be 1 or negative 1, and the absolute value of negative 1 or 1 is going to be 1. Absolute value of n is just going to be n. And that is going to go to 0 as n goes to infinity. So that absolute value theorem would say, okay, so if we drop the absolute value bars, then negative 1 to the n over n would also go to 0 as n goes to infinity. 3 is a constant, so the limit of a constant is a constant as n goes to infinity. And so we could use the sum of limits formula. So we know the limit of 3 is 3, and the limit of negative 1 over n is 0, and so this is going to be the sum of those, 3 plus 0, which is 3. If we look at the next example, the limit as n goes to infinity of 3 to the n over 4 to the n, we can connect that idea with f of x is equal to 3 to the x over 4 to the x. So the sequence 3 to the n over 4 to the n is going to agree with the function 3 to the x divided by 4 to the x on the positive integers. And so whatever 3 to the x over 4 to the x does as x goes to infinity, so will a sub n as n goes to infinity. So you can rewrite this as 3 over 4 to the x power. This is an exponential function. The base is less than 1, and so we're going to have exponential decay, which means that as n goes to infinity, or in this case, excuse me, as x goes to infinity, the function is going to go to 0. And so because the function is going to 0, so will the sequence. Okay. Now if we look at the reciprocal of that, the limit as n goes to infinity of 4 to the n over 3 to the n. And then we're going to look at the function f of x is equal to 4 to the x over 3 to the x, which can be rewritten as 4/3 to the x power. This is also an exponential function, but your base is 4/3, and that's greater than 1, and so your function is going to be exponential growth, and so as x goes to infinity, so does the function, and so the sequence will also follow suit and go to positive infinity. Okay, and let's go look at some more. Let's find the limit as n goes to infinity of 3n over cube root of n cubed plus 5. We're going to look at the function f of x is equal to 3x over the cube root of x cubed plus 5. Okay, and so we're going to maybe try to use L'Hopital's rule here, because the form here is going to be infinity over infinity. And so, or technically we're using the function to do this, but we in practice we can use the notation. This is the limit as n goes to infinity of 3 over 1/3 n cubed plus 5 to the negative 2/3 times 3n squared by the chain rule. So technically we should be doing this with the function, but we can go back and forth between the function and the sequence. Okay, so we're applying L'Hopital's rule technically to the function here and seeing what that'll do. And so this is the limit as n goes to infinity of 3 times n cubed plus 5 to the 2/3 all over n squared. And then again we try to investigate what happens when n goes to infinity. We're going to have the form infinity over infinity. So again we could apply L'Hopital's rule to the function, and we'd have the limit as n goes to infinity of 3 times 2/3 n cubed plus 5 to the minus 1/3 times 3n squared by the chain rule, all over 2n. So this is going to be the limit as n goes to infinity of 3n over n cubed plus 5 to the 1/3, and so that's going to be infinity over infinity, and actually it's back to the original limit. The expression is the same as the beginning, and so L'Hopital's rule doesn't really work on this one because we're just going to go in circles. So we have to do a different technique for limits. This was a technique certainly used in Calculus 1, where you factor out the largest power of x, and so that's what we're going to do here. So this is going to be the limit as n goes to infinity of 3n over that'd be the n cubed times the quantity 1 plus 5 over n cubed raised to the 1/3 power. And then we'll use properties of exponents to rewrite the denominator as n cubed to the 1/3 times 1 plus 5 over n cubed to the 1/3. The 1/3 power and the cube will undo each other. That's really just a cube and then a cube root. So this becomes the limit as n goes to infinity of 3n over n, 1 plus 5 over n cubed to the 1/3 power. Then we can go ahead and simplify that. Limit as n goes to infinity of 3 over 1 plus 5 over n cubed to the 1/3 power. And so now we can go ahead and evaluate this. The 5 over n cubed as n goes to infinity is going to go to 0. And so this is going to be looking like 3 over 1 plus 0 to the 1/3 power, or that limit is simply going to be 3. There's going to be other instances where L'Hopital's rule will actually work, but you got to keep in mind that we're actually using the function. So we translate it over into a function, and then we use L'Hopital's rule with the function, but we can be a little bit loose with the notation here, I suppose. All right, let's work on a couple more examples here. So we're going to look at the limit as n goes to infinity of n times the sine of 1 over n. And so we're going to pair that up with its function x sine of 1 over x. Okay. Now, when we let n go to infinity, the form of this is going to be infinity times 0, because it's going to be infinity. The n's going to infinity, and the sine of 1 over n, the 1 over n is going to 0, and the sine of 0 is 0, so that's our form. So we got to rewrite, and so we're going to rewrite this as the limit as n goes to infinity of the sine of 1 over n divided by 1 over n. And so now our form is going to be a, what do we got? A 0 over 0. So this is a 0 over 0 here. And so that's a candidate for L'Hopital's rule. So the derivative of the top will be the cosine of 1 over n times negative 1 over n squared by the chain rule. Derivative of 1 over n is negative 1 over n squared. The negative 1 over n squared is absorbed, and we have the limit as n goes to infinity of the cosine of 1 over n. So the 1 over n is going to go to 0 as n goes to infinity, so this is going to be the cosine of 0, which is 1. Okay. All right. I think we got one or two more examples here, so let's see what we're doing in example number 11. So the limit as n goes to infinity of the sine of n over n squared. Okay. So f of x is going to be the sine of x over x squared. Okay. So what we're going to do is we're going to use the squeeze theorem on this. So what we have, the sine of n is probably going to isolate somewhere between -1 and 1. That's the range of the sine, and then the n squared is going to infinity, and so we're going to have something between 1 and -1, and something really large. That's going to be 0, but we're going to use the squeeze theorem here, and we know that the sine of x in absolute value is bounded between -1 and 1, so the absolute value of the sine of x is less than or equal to 1. Okay, and it's actually also bounded by a 0, so we can put that in there. So the sine of x over x squared is going to be between 0 over x squared and 1 over x squared, and then of course we're assuming that the x is not 0. Okay, so we'll take that inequality and divide by a positive number being x squared, then the inequality is preserved. Okay, and so x is greater than 0, and so the limit as x goes to infinity of 1 over x squared, we know that's 0. And the limit as x goes to infinity of 0 is going to be 0. And so by the squeeze theorem, the sine of x over x squared, it doesn't have anywhere to go. It's bounded between those two functions that are going to 0. So the limit as x goes to infinity of the sine of x all over x squared is going to 0. And I went ahead and put the absolute value bars on it. And then we can use the fact that if the absolute value is going to 0, then so is the original function here. Okay. And so because the function is going to 0, so is the sequence that matches the function and all the positive integers. Okay. So stay tuned for the next video. I think we're going to be talking about, let me see, what are we talking about in the next video? We're going to be talking about monotonic and bounded sequences, and we'll do a little bit more theory, the completeness axiom, a theorem about monotonic and bounded sequences, and then I think we'll have a little bit of a longer, either that video will be a longer video, or we'll have a fourth video where we talk about recursively defined sequences, arithmetic sequences, geometric sequences, and we'll also look at a little bit of factorial. You would have seen factorial in pre-calculus, but it's been a while, so we'll look a little bit of factorial because it's coming up. We'll see you next time.